Namaste everyone. Welcome to current electricity chapter entrance exam classes. Hope you are all doing well and you are healthy and active. You are always sharing. Okay, so we will move on to the next questions. We have already solved many questions in many topics in current electricity. Today we will take up that meter bridge and Wheatstone's bridge. You know that Wheatstone's bridge is a collection of some resistances and they are connected in the form of a quadrilateral. So like this, we will see a little bit of theory and then we will move on to the problems. You can expect some questions from meter bridge and potentiometer for NEET examination. Yeah, and their questions are very easy, so you can solve it. So if you connect the resistances in this order, R1, R2, R3, R4, and a fifth resistor here, and if you connect a battery here, no current will flow through this. This current will be zero provided the bridge is balanced. What do you mean by balancing the bridge? It is nothing but the ratio of these resistances R1 by R2 must be equal to R4 by R3. Right? You have to take the same order. However you name it, whatever be the naming is done here, this divided by this and this one by this must be same. Or this left by right, that is also same. R2 by R3 is equal to R1 by R4. You take R2 here and R4 here, that is one and the same. So this way is also possible, this way is also possible. Divide any two consecutive resistances, neighboring resistors, but not opposite resistors. Condition for balancing is not R2 by R4 is equal to R1 by R3. So it is not so. Only adjacent anyway, but follow the same order. R1 by R4, R2 by R3, R4 by R1, R3 by R2, they are same. Okay, if that condition is satisfied, no current flows to the galvanometer, because, sir, once a component is connected in a circuit, current should flow through that now. But why it happens so here? Yes, current doesn't flow. Current flows between 2 points in a circuit only when there is a potential difference. If water is filled in a pipe, there is no guarantee that the water is flowing. Water will flow in a pipe only when there is a pressure difference. Heat energy flows only when there is a temperature difference. So if you adjust the resistances in such a way that if the potential here and here are same, then you will never expect the current. You can never expect the current through this. So it is same as if you connect the resistance here or remove it and keep it in the cupboard, result is same. No current flows through this resistor if it is balanced. Then you can continue the reduction of all these resistances and all, and you know this. So if you do it so, if you connect a galvanometer here and adjust the current 0 in the galvanometer, then this condition is satisfied. And if you know the 3 resistance in them, and if you don't know any one, you can find it out. That's why it is used to find the unknown resistance or get the ratio of 2 unknown resistors. So it has many applications. If you have selected all these resistors yourself, and if this is unknown resistor, you can calculate it. Now, this Wheatstone's bridge is made into a miniaturized form, or it is made into a ready-made form in meter bridge. You know that in meter bridge consists of a L-shaped 2 strips, not single one, 2 strips like this, and a single strip here. You did the experiment in this, and here is a wire, and this is a meter bridge wire itself. That is 1 meter long. That is why it is called meter bridge, and this serves the job of these two. R1 and R4, that role is played by this wire. That wire can be cut anywhere, or it can be broken anywhere, or it can be taken as 2 resistors by connecting it anywhere in between. And so that wire totally plays the role of R1 and R4. So I will just elongate it a little bit. So like this. Now this is the wire which is connected, 1 meter wire. And where is the R2 and R3? R2 and R3 will be here. So this one. So this is R2 and this is R3, and you can divide this wire into 2 parts. Say this is resistance of this part of the wire is say R1, and the resistance of this part of the wire is R4. So R1 and R4 are connected here, R2 and R3 here, and the point where R2 and R3 are connected, one end of the galvanometer comes here, and the point where R1 and R4 are connected, the other end of the galvanometer reaches here. So this is the jockey, you know, you can move the jockey over the wire and you can connect it anywhere till the galvanometer shows zero deflection. Of course, if all these things to happen, you need an energizer, that is battery. Battery has to be connected here at the end points of R1 and R4. End points of R1 and R4, you have the battery. So this battery of EMFE. And remember, balancing condition doesn't depend on the battery, because only some current should flow such that potential here and potential here are same. No potential difference, so no current flowing through the galvanometer. Okay. So now, in the practical part, you use the formula like this. You change the symbols, I change the symbol like this, and you name this as R, and this is standard resistance box, and this is taken as balancing length L, and you know that resistance is directly proportional to length R equal to rho L by A. Since this wire is uniformly, it's a wire of uniform cross-sectional area, A is same for both the pieces and rho is same for both the pieces, both are made up of the same material, so L is enough. You can, the ratio can be written as L by L. Since it is 1 meter in length, 1 minus L, you can write it like this. This is the remaining length. So if the bridge is balanced here, then you can write the formula. I will write it here only. R by S, this by this, right, is equal to this by this. L by 1 minus. Actually, this one rho L by A, rho into 1 minus L by A. Rho by A gets cancelled. So L by 1 minus L. So R equal to SL by 1 minus L. You may be remembering that formula that you have in your brain for the practical exam. So that is the formula, and unknown resistance can be calculated using this one. Now the thing that you have to know here is, when this is a balanced Wheatstone's bridge, now what happens is, I will remove all these unnecessary values. Suppose in the problem, if you get things like this, this condition R by S is equal to L by 1 minus L. So in this ratio, if this ratio has to be same, if R is much more, then L should also be more, right, compared to 1 minus L. If R is much greater than S, then L should be much greater than 1 minus L. If the ratio is same, suppose R is 4 times greater than S, L should be 4 times greater than S. So if this resistance is more and more, you will have more and more balancing length this side. If this resistance is more and more, you will have more resistance and more balancing length from this side. Suppose both are equal, then these two will be equal. They will be equal only when the balancing length adjusts at 50 centimeters, that is 0.5 meters. So if both the resistances are equal, balancing length is exactly at 50 centimeter. If R is less, balancing length will be within 50 centimeter. If S is less, balancing length goes, because length is always measured from the left side, balancing length goes beyond 50 centimeter if this is less. Another thing, suppose this is the condition when suppose if the problem runs like this. When a resistance is balanced in a Wheatstone's bridge, balancing length is found to be 40 centimeters. When another coil is connected in series with the resistance on the left gap, balancing length changes by 10 centimeter. Did you follow my sentence? A bridge is balanced, Wheatstone's bridge is balanced at 40 centimeter for some resistance R. If a series resistance is connected along with R, a coil of certain resistance is connected in series, balancing length shifts by 10 centimeter. They have not given, it gets increased by 10 centimeter or decreased by 10 centimeter. That sentence is not available. The balancing length changes by 10 centimeter. If it changes by 10 centimeter, shall we add 10 or subtract 10 from original 40? That is the question. You must get it from your knowledge. If a coil of resistance X is connected in series with this one, what happens is total resistance of this end will increase, because in series resistance will increase in series connection. Definitely this balancing length should become more, so it should be 40 plus 10. Suppose you connect a series resistance here. What happens? If you connect a series resistance here, resistance on the other side will increase. This will increase, that means this will decrease. 40 minus 10. Suppose a parallel resistance is connected. A coil is connected in parallel with the resistance on the right gap. When the balancing length changes by 10 centimeter, original balancing length is 40. So what you will take? 40 plus 10 or 40 minus 10? A coil of resistance, certain resistance is connected in parallel with the resistance on the right gap. When this is connected, parallel combination always reduces the resistance. So this resistance will reduce, balancing length will reduce. This will increase by 10 centimeter. So this idea of adding or subtracting, what happens to the balance length, all things are needed in meter bridge. That's all you have to know. And again, another thing is equivalent resistance of a meter bridge circuit, that Wheatstone's network. Usually that value of when all the resistances are equal in a Wheatstone's network, this is R, this is R, this is R, and this is R. When all the resistances of a Wheatstone's network are equal, then if you have the fifth resistance R here, even if you connect a battery, no current will flow to the middle one, because you know it is balanced already. R by R is equal to R by R. So what is the use of keeping this R here? No use. You can remove it. Even if you keep it in your cupboard, and even if you connect it here, no current will flow through that galvanometer path or resistance path in the center here, from here to here. Now what is the equivalent resistance between these 2 points where battery is connected? Equivalent resistance between these two is 2R, R plus R, 2R. 2R parallel is 2R by 2, because 2R into 2R by 2R plus 2R. Anyway, you can write it. That is R. So when all the resistances of a Wheatstone's network are same, then equivalent is also R. So that is about Wheatstone's bridge. And another thing, some circuits don't appear as if they are Wheatstone's network, but they are sometimes. So how to analyze it? Only the thing is you have to train your brain, and we are going to discuss about all these types of circuits in a separate unit. We will do that, and you can take it like a puzzle, and you can with some interest you can solve it. So suppose it's, for example, a simple circuit I will show which doesn't look like Wheatstone's bridge. You might have seen this circuit anywhere, in some of the books. One resistor and another resistor here, another resistor one here, and suppose this is A and this is B. This is a Wheatstone's network. So all the resistances values are R, equal resistances. Now what you have to do is just stretch this one away, with keeping these connections as it is, and without losing these connections, without losing even this connection, just place it somewhere here. So just bring these two resistors on the other sides, and then what happens? So if I just try to pull it away, then that triangle remains the same. That doesn't change at all. Okay, triangular shape of connection remains the same. When this part is pulled out here without losing the connection, so it will be like this here. So this part of the resistance is here now, and this part of the resistance is here, and A will come to this side, and this is A, and I'll stretch B also. B will come here. Now does it look like Wheatstone's bridge? Just turn it like this and you will get it as Wheatstone's bridge. Its equivalent is R. So some of these circuits, I don't waste my time by drawing all those circuits here. We will do it in PPT, PowerPoint presentation. That becomes easier. So we will have a separate 1 or 2 classes for finding the equivalent, and you will have some complicated circuits also. So now we will go back to the problems related to meter bridge. Then we will go to potentiometer. Okay. First problem. Yes. You don't have very tough problems here. You will have very good problems here, which can be worked out very easily. With a resistance P ohm in the left gap and another resistance Q ohm in the right gap of a meter bridge, the balance point is obtained at 40 centimeters. When a resistance of 6 ohm is connected across Q, where is Q? On the right hand side. The balance length shifts to 50 centimeter. The value of P is. So you have to go on writing, you should go on writing the formulas for each step. With a resistance P ohm in the left gap and another on Q on the right gap. That means P by Q I can write. Balancing point is 40. 40 by 100 minus 40. I will take it as centimeters. So L can be L by 1 minus L or L by 100 minus L, provided L is in meters or centimeters. When a 6 ohm resistor is connected across Q means parallel to Q. That means its total resistance decreases. Balancing point shifts to 50 centimeter. The value of P is. Okay, we will do that now. Right. So there is a meter bridge. I will write only the values. Resistance P in the left gap, Q in the right gap. Balancing point is at 40 centimeters L, and this is 100 minus L is 60 centimeter. So if I want to write the formula, P by Q is equal to L by 100 minus L. What is P? 40 by Q is 60. Sorry, P by Q is equal to 40 by 60. That is 3 times and 2 times. So you got the relation between P and Q. So they have asked you to find out the value of P, not Q. So I will substitute for Q so that P remains. So what is Q equal to? Q is equal to 3P by 2. So let it be the first equation. Next they say that if a resistance of 6 ohm is connected across Q, so for Q I will connect 6 ohm resistance in parallel. Okay? If I connect a 6 ohm resistance in parallel, this resistance reduces and the balancing length is shifted by 10 centimeters, something like that. They say that the balancing length shifts to 50. Okay, they have given new balancing length. So this is 50, then this is also 50. So the new value, this one. So what is the new formula? Now P divided by 6Q by 6 plus Q. What is this 6Q by 6 plus Q? That is the parallel combination that is on the right hand side. A 6 ohm resistance is connected in parallel with Q. Yes, that is equal to 50 by 50 because balance length shifts to 50 centimeter. Remaining 50 is on the other side. Now we will substitute for Q because they want P. So let us have only P in the formula. P into 6 plus Q divided by 6Q is equal to 1. ಸ್ವಲ್ಪ ತೀಗನಿಲ್ವಾ? Yes, so P into 6 plus Q by 6Q is equal to 1. Now let us substitute for Q and I will rearrange it. P into 6 plus Q is equal to 6Q and then P into 6 plus Q is equal to 6 into, okay, I can substitute for Q also. 6 plus 3P by 2 is equal to 6 into 3P by 2. PP gets cancelled here. So what is remaining? This is 3 times. So this is 9. 6 is equal 6 plus 3P by 2 is equal to 9. That is 9 on the right hand side. So 9 minus 6 is 3. 3P by 2 is equal to 3. 9 minus 6. 3 gets cancelled. So P is equal to 2 ohm. That is the answer. So P is equal to 2 ohm. So if you go back to the problem, you'll get the answer 2 ohm. It's the fourth option which is correct. Option number 4. So simply you have to know what is the how to convert that 6 ohm connected parallel, how to change it with the balancing length. Of course they have given direct the balancing length 50 centimeter. Even you must know that it should become 10 centimeter more. Okay. Okay, we will go to the next problem. Yeah. 2 resistances are connected in the 2 gaps of a meter bridge. The balance point is 20 centimeter from 0 end. That means left end. A resistance of 15 ohm is connected in series with the smaller of the 2 resistances. So there is one more challenge. You have to find out which is the smaller resistance. A resistance of 15 ohm is connected in series with smaller of the 2 resistances. When the null point is shifted to 40 centimeters. The smaller of the 2 resistance has the value in ohms, right? 2 resistances are connected in the 2 gaps of a meter bridge. We will take them as P and Q. Okay, P on the left hand side, Q on the right hand side, and the balancing point is 20 centimeter. If this is 20 L, then this is 80, which is 100 minus L. 80 centimeter, which is 100 minus L. Okay, that is and you can connect them by a formula. What you can do, P by Q is equal to 20 by 80, that is 1 by 4. That means Q is equal to 4P, right? 4 times P is Q, so Q is greater, P is smaller. Because you have to multiply P by 4 times, then you get Q. So Q is greater than P, right? So Q is greater than P. That means they are asking you to find out the smaller of the 2 resistances. That means you have to find out P. P you have to find out. Okay. So one relation we have got, 4P is equal to Q. Okay. A resistance of 15 ohm is now connected in series with the smaller of the 2 resistances. That means 15 P ohm. A resistance of 14 ohm, a resistance of 15 ohm is connected in series with the smaller of the two resistances. Now the null point is shifted to 40 centimeters. This is 40 when this is connected here. So P plus 15 you have here. You have Q here, and then this is 60 centimeters. This is the new value. So when 15 ohm resistance is connected in series with the one of smaller of the two resistance, balancing length shifts to 40. It is not shifting by 40. So if it was shifting by 40, then you should have written 60 here, 40 plus 20. It shifts to 40. So what is the smaller of the two resistance? We can write the new equation. P plus 15 divided by Q must be equal to 40 by 60. That is equal to 2 by 3. Okay, P by Q is equal to L by 1 minus L. Okay, now you have to find out what is the P. So substitute for Q. So I can rearrange this. 3P plus 45. 3P plus 45 is equal to 2Q. Substitute Q is equal to 4P. Q is equal to 4P. 3P plus 45 is equal to 2 into 4P. This is 8P. 45 is equal to, this is 8P minus 3P. 8P minus 3P is 5P. What is P is equal to 9 ohm. So that is 9 ohm. Option number 2. That is the correct one. So again, the same technique. Calculation is not much tougher. It's very easy calculation. Only the idea is whether we have to increase the balancing line, decrease it, or that is surely given here, no problem. But how to proceed with after connecting the resistance of 15 ohm in parallel, in series and all. Okay, so option is second one, 9 ohm. We will move on. Next question, 78. Yes. An unknown resistance R1 is connected in series with a resistance of 10 ohm. The combination is connected to one gap of a meter bridge, okay, while the other gap is connected to another resistance R2. The balance point is at 50. Now when the resistance of 10 ohm is removed, the balancing point shifts to 40. The value of R1 in ohm is, okay. Another same type of problem. An unknown resistance R1 is connected in series with 10. So what do you have on the left hand side? R1 plus 10. We will come back to the board. Unknown resistance R1 is connected to the 10 ohm resistance in series. Combination is in one gap, say left gap, while the other gap is connected to resistance R2. Okay. Now the balancing length is 50. What do you mean by balancing length is 50? Then here also 50. You know that it is left hand side, right hand side resistances are same in the meter bridge. So R1 plus 10 by R2 must be equal to 1 because it is 50 by 50, that is equal to 1. R1 plus 10 is equal to R2. One equation. Okay. What is the next part? The balancing point is at 50. Okay. Now when the resistance of 10 ohm is removed, the balancing point shifts to 40. Okay, it should be reduced because when you reduce this by removing 10, balancing length from this side should come nearer, and here it should increase. Okay, now the new values of resistances are, they are like this. Okay, the resistance is R1 here, R2 here, and the balancing length is 40 and 60. It reduces to 40. R1 by R2 is equal to 40 by 60, that is equal to 2 by 3, 2 times, 3 times. Okay, then what is the new equation we have? 3R1 is equal to R2, 2R2, sorry. 3R1 is equal to 2R2. Now the question is, then the value of R1 is. So shall we substitute 2R2 is equal to 3R1. We will take this equation. I will take this equation and I will multiply by 2 because I have 2R2 here, so that I can substitute it. So multiply by 2. What I will get? 2R1 plus 20 is equal to 2R2. 2R1 plus 20 equal to R2. Now bring this 2R2 here, 3R1. Then the whole equation will be R1. So 2R1 plus 20 is equal to 3R1. You bring this R1 here, 20 is equal to R1. So R1 is 20 ohm. 20 ohm is equal to R1. That is the answer. Option number 3, correct? It is option number 3. Yeah, going back to the problem, it is 20 ohm. So similar problems with small differences, that's all. Okay, we will move on to the next one. Yes. 5 resistances are connected as shown in the figure. ABCD, you can see that. The equivalent resistance between A and C is, A and C, okay. It is a balanced one. Actually, A and C should be here. So it has been shifted, that diagram is shifted a little bit. A is here, C is here. Please correct it yourself. This is A and this is C. This is B and this is D. Now see whether it is a balanced network or not. And this is the point where you connect the battery. Usually, if at all some equivalent resistance is asked between 2 points, that does mean that you are going to connect a battery across it. So here you are going to connect a battery. Whether it is balanced, you just see that. 2 by 3, is it equal to 4 by 6? Yes, it is balanced. 2 by 3 and 4 by 6 is also 2 by 3. So it is balanced. So what is the use of keeping this 7 ohm here? You can remove it and throw it away, because even if you keep it here, no current flows through it. So you can keep it on your table, no current flows even now. So remove it. What you will have between A and C now? Between A and C you have a 5 ohm on upper side, 10 ohm on the lower side. So 5 parallel 10, what is that 5 parallel 10? 5 into 10 divided by 5 plus 10. 5 into 10 is 50, 5 plus 10 is 15. 50 by 15 is almost 3 times, or 50 by 15 can be written as 10 by 3, right? So is it this one? This option. I think I need not use the board at all. This option, 10 by 3, 50 by 15, 5 3s are, 5 10s are, right? So very easy problem. Okay, but this is a basic so that I can move faster later in equivalent circuits. Okay, here you see, all of a sudden we can't jump into the conclusion that every circuit is a Wheatstone's network. That is not possible. Okay, sometimes you must be very careful. Here is a problem. Potential difference between the points P and Q in the circuit is very simple. And again I say, you must have this circuit in your one hand, because don't waste your time by keeping on drawing all these things. That is a waste of time. You are not going to get anything after drawing this. Just understand the problem and solve it. So I have the PDF form of all these questions. If you want, you can send a message to this one saying that you want a PDF form of this question paper. Don't message to this number simply, sir, I want the question paper, because I don't know which question paper you want, whether it is SSLC question paper, whether it is theory question paper, whether you want CET question paper. You mention your name and send the details. Then I'll send the PDF form of this question paper so that it becomes easier to discuss the question. Potential difference between the points P and Q in the circuit is, so I will draw it here. Okay, I'll draw it very quickly, like this, like this. Here you have a circuit which looks like Wheatstone's network here, but you can't treat it as Wheatstone's network. So here some current is given, that is 1.5 amperes enters into this one circuit. P is here and Q is here. Okay, and resistances are 2, 4 and 3, 6, 12. 3, 6, 12. Everything in ohm. Okay. Yes. Now, their question is potential difference between P and Q. What is the potential difference between P and Q? Suddenly don't come to the conclusion that it's a balanced Wheatstone network. So, because 2 by 4 and 6 by 12 are balanced, but provided, very, very important point I'm saying here. This is not a Wheatstone's network, because you have connected the battery here. You have connected the battery here. So since you have connected battery here, it becomes and the fifth resistor is not connected here. Am I right? Because they have given the direction of current here. The current direction is like this. This current direction will be obtained only when you connect the battery like this. Otherwise, how can you get the current from this side if by connecting a battery here? It's not possible. It should be like this. So that current moves out here. That is what is given. Now, if the battery is connected here, this will act like a Wheatstone's bridge only when this resistor comes here. This 3 ohm must have been here. So this is not a Wheatstone's bridge. This is simply a circuit, some type of circuit, because it is not satisfying the rules of the Wheatstone's network. So there is no question of balancing at all when it is not a Wheatstone's bridge. Okay. So then how to solve this? Simple, very simple circuit. What is the potential difference between P and Q? Only simple way, current into total resistance, because this 1.5 will pass through all the three resistors. Squeeze it and reduce it into a single form. Then it is finished. So how many resistors are there in the parallel path? One is 8 from here to here, because current is flowing like this. This is series, and all the three parallel. So you have three resistors. One is like this, another is like this, okay, and the third one is like this. And this is 8, and this is 16, and this is 3 ohm. All the three in parallel, and this is 1.5 amperes. Now what is the equivalent? That we will find out. Then I into R, that's all. So V equal to IR. What is R? 1 by Rp is equal to 1 by 8 plus 1 by 3. I'll do it like this time. Or do you have any direct method? Yeah, I think it is possible, right? First you make a parallel combination with these two, and then with the remaining one. 8 into 16 divided by 8 plus 16, 24. Is it right? Okay. 8 into 16 divided by 8 plus 16. This is 3 times. Oh no, it becomes a, okay, this is 16 by 3, let it be. 8 into 16 by 8 plus 16, so 3 times 16 by 3. Then 16 by 3 parallel 3. 16 by 3 into 3 by 16 by 3 plus 3. I would have continued in the same process, 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is also possible, but anyway, I can do it like this way also. Okay, this gives, this is 16 by 3 into 3 divided by 16 by 3 plus 3. Okay, let it be like this way only. 16 by 3 into 3 divided by, what is this? These are 9, 25 by 3. Am I right? 25 by 3. Yeah, this is 3 ones are 1, 3s are 9, 25 by 3. So by 3 gets cancelled. So what is remaining? 48 by 25. So 48 by 25 is the equivalent resistance. Am I right? This one series and all the three parallel. Once it is 48 by 25, see here we have used R1 R2 by R1 plus R2. You need not invert it again. What is potential difference between P and Q? 48 by 25 R into I. V is equal to IR. IR is 1.5 amperes. So I think I have a fraction of currents. Yes, we have 5 5s are 5.3s are. And this one is 5 1s are 5.06 are. So multiply this one here. What is the answer now? That is equal to 40, 60, 6 into 8, 48, 4 remaining, 24, 28, and how many places to? 2.88 volt. That is the answer. We have that answer? Yes, thank God we have the answer. That one, second option. So very simple logic. Find out the total equivalent resistance, multiply it to the current, that is the voltage. But there is a danger that once we will see the question, there is a danger that once we are addicted to these Wheatstone's network, there is a chance of treating this as a Wheatstone's network. But see that carefully, it is not a Wheatstone's network, because once the resistor is connected to two opposite sides of a quadrilateral, battery should be connected to the remaining two opposite sides, but it is not done here. Current is flowing here. So you will never treat it as a Wheatstone's network. Simply you have to calculate IR. So answer is this one. Shall we move to the next one? Okay, so yeah, right. In a meter bridge experiment, null point is obtained at 20 cm from one end of the wire when resistance X is balanced against another Y. X is less than Y, they have given. But this data, X is less than Y, is a very foolish data, because we are brilliant now. You know that the balance length is 20, so definitely X is balanced again. Okay, they have not given which one is which side, so better I think you have followed it. It's a brilliant data. So we can't conclude, because they have not told where X is connected and where Y is connected. Okay, let it be. So since 20 cm is the balancing length from the left hand side, X should be on the left hand side. X is less than Y. Then where will be the new position of the null point from the same end if one decides to balance another 4x against y? Oh, you have to replace x from 4x. That means you have to add in series 3x. How much is that balancing length? So we will do that. We will write the equations for both the cases. It is same as the previous sum problems. So now balancing length is 20 when x is balanced against y. So I will put x here, y here. This is 20, this is 80. So what is the equation? X by y is equal to 20 by 80. That is equal to 1 by 4. What does it mean? 4x is equal to y. So y is greater than x. When x is made 4 times, you get y. Okay. Now, next, what you have to do? In a meter bridge experiment, null point is obtained at 20 centimeter from one end, and x is balanced against y. Now, what will be the new position of the null point from the same end if one decides to balance a resistance of 4x against y? 4x against y. That means if this is 4x and this is y, and I think you can conclude this because y itself is 4x. If this is 4x, y is also 4x. Balancing length should be 50, right? Because they are equal resistances. So L and 100 minus L. I don't know what is L. So divide them. 4x by y is equal to L by 100 minus L. What is y? Take y as 4x. 4x by 4x is equal to L by 100 minus L. And of course this is 1. Then you can continue this one. 100 minus L is equal to L. 100 is equal to 2L. Minus L becomes plus L. L is equal to 50. Of course we have concluded it here only because when y is made 4x, this x is made 4x, y is automatically 4x, already it is 4x, so they become equal. Balance length is 50 centimeters, very easy problem. But remember, it was once asked for medical exam, I think somewhere, I haven't mentioned it long back. So very easy problems will also be asked, okay? Okay, we'll move on to the next question. 82, yeah, here. Yes, so this is a peculiar problem now. Yes, in the circuit, if no current flows through the galvanometer, that means it is balanced. When the key is closed, bridge is balanced. Balancing condition is right. But we have a special guest now, that is capacitor. Usually we have resistors in our problems. Now there is a special guest, that is capacitor. So how to continue with capacitor? You know that capacitor offers resistance to the flow of AC. You have to go to that response of AC with the capacitor, inductor and resistor. It gives resistance to AC also. It gives resistance to DC also. Now, what type of resistance? And you know that reactance, suppose coming back to the board, so I will write the same circuit. There are two resistors here. It's a balanced Wheatstone network. They have said it already. This is here is a capacitor of capacitance C1 and here is a capacitor of capacitance C2. Of course, everything is connected. Now, so how to write the balancing condition for this one? It is the resistance of first resistor by second resistor is equal to resistance of capacitor 1 divided by resistance of capacitor 2. Actually, this is XC. You remember reactance of a capacitor. But what about the reactance of the capacitor? You know, reactance of any capacitor is 1 by 2 pi nu c. It is inversely proportional to capacitance. So reactance of the first capacitor by reactance of the second capacitor equal to resistance by resistance. So R1 by R2 is equal to C1 by C2 if it is balanced. Sorry, XC1 by XC2. Now how can I write it? R1 by R2 is equal to, what is XC1? It is 1 by 2 pi nu C1 here, right? 1 by 2 pi nu C1. What is XC2? 1 by 2 pi nu C2 here. So is this the balancing condition? So in a capacitor circuit, before going to the problem, I will discuss if all the components are capacitors, what will happen? Suppose 2 are resistors, 2 are capacitors. So R1 by R2 is equal to C2 by C1, because if all the components were resistors, R1 by R2 is equal to R3 by R4, something like that. But here you have ulta ratio, right? Because reactance is inversely proportional to capacitance. Okay. Now if all the components are capacitors, how will you write the balancing condition? Like this. It is as usual. Why? Because everything is inversely proportional to the other one. C3, C4. Now, resistance of this 1 by C1 by resistance of this 1 by C2 is equal to resistance of this 1 by C3. 1 by 2 pi nu I will cancel, right? By resistance of this 1 by C4. Because 1 by 2 pi nu C, 1 by 2 pi nu C, 1 by 2 pi nu C, 1 by 2. So is it not same as C1 by C2? Okay, you can rearrange this. C1 by C2 is equal to C3 by C4. Because everything will get inverted. The whole formula gets inverted. So you can invert it again. You will get the same condition as the resistors. So, and remember that also holds good. Okay. So if all the components are capacitors, no problem. If the only two are capacitors, remaining are resistors, then get the reverse ratio of resistance, capacitance for reactance. So reactance is Xc is 1 by 2 pi nu C1 and Xc2 is 1 by 2 pi nu C2. So here 2 pi nu and here 2 pi nu, that gets cancelled. Okay, now another thing to be noted here is if all the values of capacitances are C, what is the equivalent value? That is also C. But sir, in capacitance and resistances, the formulas interchange, right? In resistors, series combination R1 plus R2. But capacitance, series combination C1, C2 by C1 plus C2. See, in the same way in parallel, it is interchange. How does it result in the same 2C? Because we have seen, if all the if all the resistors are R values, then the equivalent resistance is R. If all the capacitors are C values, what is the equivalent capacitance? C only. Okay. You will get the result. What is this? C series, C by 2, C by 2, C series, C by 2, C by 2 plus C by 2, C. Because even if the formulas are interchanged, you will use both. You will use it once series, once parallel, as you do it in resistors. So you will get the same answer. So if all the capacitors are C in a Wheatstone's network, the resultant equivalent value is also C and it is balanced. Okay, now here what is the answer? We didn't go to the problem. R1 by R2 is C2 by C1, right? R1 by R2 is C2 by C1, or R2 by R1 is equal to C1 by C2. Option 4. It is option 4. Going to the problem, it is option 4. R2 by R1 is equal to C1 by C2. Very simple problem, and we will have to see all the possibilities related to this problem. So option 4 is the correct one. C1 by C2 is the reverse ratio of resistance. Okay. Moving on to the next one. Yeah, potentiometer. We will see the potentiometer in the next class, right? We will shift it to the next class. Okay, we will continue it in the next class, potentiometer. I think by potentiometer and another one, that is some sets of connections of voltmeters and ammeters, we will finish one set of revision for current electricity. Then we will move on to the different chapters. Okay, so keep going and look into these questions so that you will understand more when I give the explanations. Try these questions. We will meet in the next class. Thank you.